And then, yeah, we'll drop off now, and then we'll start in a moment. Okay, good afternoon and good morning to the people out west, and good afternoon and welcome to the people from overseas as well. Thank you for joining ASIC's webinar series number 43, which will be covering geosynthetic solutions for subgrade stability under cyclic loading under railway applications. And we're pleased to have this presented by Professor Cholachat from the University of Technology in Sydney. Gone one too far. So ASICS is part of the wider international community known as the International Geosynthetic Society. So that's an international membership, and then there are 45 local chapters globally representing 50 different countries. With over 40,000 members, including corporate individuals and students, so it really is a wide community. And recently here in Australia, we hosted the Asian regional conference, which was exceptionally well attended, which happens every 4 years. And the next one will be in the country of India. So our local chapter in Australia, or ACIGS as it's known for short, to become a member, you then get access to a lot of resources, a lot of tools, special events as well that you can get invited to. You can join as an individual, you can join as a student, which is actually free of charge, or as company or corporate members. And a few of the benefits that go on, so we do a couple of initiatives. One of them is known as a job shadowing program, which you can apply online on our website. That is literally just 1 day or 2 days potentially, where you get to go out in the field, you get to learn about the use of geosynthetics, and you get to be shadowed by experts in the industry. And you can do it from job sites, you can do it from laboratories, you can do it from consulting design offices as well. And then we go a step further where we do an actual full internship, which is approximately 3 months over the summer period. So this is where you actually work and get paid by ASICS to actually learn about the industry. So again, similar things. It could be about manufacturing, it could be about supplying, construction, designing, testing. There's lots of different avenues. The only thing is you do need to be an ASICS IGS member. And as I say, but for students, this is free of charge. So we strongly encourage you to do it while you're studying and learning at the university, because it will give you that broader, wider experience. And this can be done on the ASICS website. You just need to fill in your expression of interest. Obviously, we'll look at geography, location, and what you're studying as to what's potentially the best option for you. Okay. Now, on to today's webinar. So Professor Cholachat, I've had the pleasure of working with for better part of about 7 years, I would say, roughly. He's leading expert in geotechnical engineering, currently serves as a professor at Transport Research Centre, or UTS. Extensive experience in infrastructure research, particularly in transport geotechnics, and worked very closely within industry partners such as SMEC Consultancy, Transport for New South Wales, Global Synthetics, Douglas Partners, Polyfabrics, all about improving public transport safety. Published over 270 research articles and contributed to the Australian standards of AS 8700 on vertical drains in soft soils. Highly recognised for his contributions to sustainable infrastructure and received multiple awards, including the ISS MGE Young Member Award and the DH Trollope Award. And finally, just to say, please post any of your questions in the Q&A section on the Zoom, and we'll address these at the end. And if so required, you can also get a certificate for attending today's webinar, which will go to part of your engineering points. With that, I'll stop sharing my screen and please hand over to Professor Cholachat.
Andy, can you see the full screen?
Yes, I can. Sorry, yes. Yep.
Oh, good. Yep. Okay. Right. Okay. Good morning and good afternoon, everyone. Today is my pleasure to be here with AXIC seminar, and I just want to thank Andy and Roger for creating this opportunity for me to represent the UTS-TRC and present some interesting research work in terms of the application of geosynthetics for soft subgrade stability under the railway condition. Right. For the, let me change the, for Australia, we have to acknowledge the country. We would like to acknowledge the Gadigal people of Eora Nation, the Burungal people of Darang Nation, the Bidyago people and Gamagal people upon whose ancestral lands our university stands. We would like to pay respect to elders both past and present, and acknowledging them as the traditional custodians of the knowledge of this land. Right. For today's presentation, we will start looking at the issue of subgrade fluidization or the mud pumping in railway, and investigate the role of the geotextile using our unique large-scale dynamic filtration tests under the cyclic loading. And we are going to evaluate the performance of the geotextile in terms of reducing excess pore water pressure as well as controlling the fine particle migration. After that, after we learn about mechanism, we should be able to see the development of the numerical models which can be used in the real case study and the future project to analyze how the geotextile filtration and drainage behavior affect the soft subgrade soil. And also at the end, we will have some user-friendly software that can be presented for the industry application. Right now, for today's presentation, we are going to discuss about the mechanism of the mud pumping that still need some further understanding. How can we differentiate this from the undrained yielding, and also prevent this to ensure that we can minimize the maintenance costs for the railway that is under operation. And also we are going to look at the solutions where we try to improve the drainage capacity of the entire track using the application of the geosynthetics. And how can we select appropriate design of geosynthetics to make sure that it can fulfill the performance of application in the railway engineering. Right. Now, with the initial site investigation for the railway line built on the eastern coast of New South Wales, which mainly soft subgrade soil, Nguyen and Indraratna has investigated the entire length of this railway track, and they found out that on and off you have spot where you can observe the ballast fouling, which occur due to the pumping of the soft subgrade from the underneath railway track. And you can see from the picture on the right hand side where you can observe that the ballast particles are mixed with the fine that has been pumped from underneath. Right. Continuing with the site investigation, we start doing the cross-section analysis. And as you can see that when we looking at the problem of the ballast fouling, start digging down, get the sample, you can see that the photo that of foul ballast that has been filled with the fine grained soil from the subgrade that pump up, as well as the damage from the sleepers. And you can see that the existence of the ballast particle is no longer exists. It's become practically the entire area has been filled with the fine particle from the subgrade. And when the worst case comes, this is observed in the freight train line in Canada, where you have excessive foul ballast in this area, and there's nowhere that the fine particle can migrate. Then it can create what we call the actual mud pumping, where when you run the train on the track, we can see the actual ejection of the fluid and fine during the process of the train itself. And quite often we try to prevent this to happen even beforehand. Right. Based on the investigation, we find out that these are the typical soft subgrade soil that can have the potential for the mud pumping, where this is a typical size of the particle size distribution, as well as the crucial properties that we need to consider, which is the combination between plasticity index and liquid limit. As you can see that the liquid limit is the index where indicate that if the water content or the moisture content of the soil reach that value, then the soil can behave like fluid. And that's why we term it as fluidization. Based on the site investigation and the data that we have from the previous study and the current study, we see that the liquid limit is quite relatively low, in the range of 30 to 50%, as well as the plasticity index, which is very narrow area as well, which is around 20 to 30%, which means that with this type of soil has the potential to mud pump easily, and it can create instability of the track itself. Now, with the collaboration with the global synthetics, we come up with the unique testing equipment where we can accommodate the larger sample of the soft subgrade soil, as well as the ballast above it. Together, we can install the geotextile at the ballast and subgrade interface, and with the actual measurement of the excess pore water pressure settlement, as well as we can apply cyclic loading on top of the soil sample and observe the change in terms of settlement, as well as the excess pore water pressure within the soil sample. The soil sample collected from the mud pump site and reconstituted and bring it back into the laboratory so that we can study the mechanism and the causative effects from this cyclic loading on the soil sample. Right. Now, on the right-hand side of this slide, this is replaced by the schematic diagram. You can see that the size of the sample is around 240 millimeters in diameter, and we can install the ballast on the top of the subgrade. And there is a option that we can provide the geotextile in between the ballast and the subgrade soil. And within the subgrade soil, you can install miniature pore water pressure transducers, as well as the other instrumentation to measure the change within the soil sample, rather than giving the overall behavior of the sample. Right. Now, let's look at what we observe from the laboratory when we start apply cyclic loading. One of our students, Valenton, has conducted the interesting one-dimensional cyclic loading on this subgrade soil. With this experiment, right, we put the intermittent sand layers in between of the soil subgrade soil layers, and to make this as the indicator whether fluidization is happening. You can see that the transition between the initial condition where you can see the individual layers of the sand layers clearly, and after a certain number of cyclic loadings, the top layers disappear and mix with the fine clay particle. You can see that we can conclude that the upward particle migration has happened because the color of the sand layers at the bottom of the sample still remain intact and does not change the color at all. You can see that because of the upward migration during the cyclic loading, it's changed the color of the sand layers itself, and suddenly the sand layers disappear at the end of the test. Right. Now, apart from this last sample, we also observed this fluidization happening during the undrained cyclic loading in the triaxial test. You can see that the failure mode under the fluidization, the failure happened at the upper portion of the clay sample, and once we complete the cyclic loading, you can take the top pedestrian out and you can observe the fluid-like sample at the top of the sample, and showing that this is there is transition from the solid state to become a fluid state at the end of the test after we apply the cyclic loading. Right. Now, when we subject this soil sample under cyclic loading, what we observe as what we expect is we can observe the increase in excess water pressure with the number of cycles that you apply along the, and some sample fail when the mean excess pore water pressure is close to 1, some is stable. And this is these are the samples subject to the different cyclic stress ratio, which is the ratio between the derivative stress in terms of cyclic load divided by 2 times of the confinement. And the higher derivative stress means that the higher axial load of the train that applied to the soil sample. And the next one, what we observe is that some sample, if they are stable, then they can develop very minimum axial strain, while the sample that experience the instability, then the axial strain itself shoot up with a short number of cycles itself. These two may not be able to explain the phenomena of the fluidization under cyclic loading unless we plot the role of the applied derivative stress together with the development of the axial strain. Let's consider the rate curve here, which is a stable sample. You can see that under relatively low CSR, the axial strain is minimum and the Q cyclic is constant, and there's not much change for the stable sample. However, there are two types of failure that the sample can experience. First one is the yielding, where the sample reach the critical state and fail. And this can be observed in terms of the green line here. You can see that the Q cyclic can be maintained throughout the application of the loading, and afterwards, once it fails, you can just observe the significant increase in the axial strain and its sudden failure. However, if you check the fluidized sample here, you can see that with progression of the number of cycles, the Q cyclic, the applied Q cyclic cannot be maintained because the stiffness of the soil has changed along the number of cyclic loading and it's getting softened. And this one shows that with individual number of cycles, you can observe significant development of the axial strain and also the softening of the sample along the way upon the fluidization of the soil sample here. Right. Now, after the testing, we extract the soil sample. For the fluidized soil sample, what we observe is that we get the soil sample and conduct the particle size distribution curve here. The red curve representing the original PSD curve before testing, which is expected to be uniform throughout the entire depth of the clay sample. And you can see that after the fluidization, the particle size distribution on the top portion contain more finer fraction compared to the particle size distribution at the bottom of the sample, showing that there is a movement, there is a migration of the fine particle from the bottom portion to the top portion of the sample. And also, apart from this particle size distribution, we also measure the moisture content of the sample at different depths. And it shows that for the fluidized sample, the water content has approached the liquid limit, while the stable sample and other sample, the water content still remain constant throughout the entire depth of the sample. Based on this observation, we can characterize and differentiate the mechanism of the instability of the undrained yielding sample and fluidized specimen under cyclic loading. When we subject the soil sample under cyclic loading, then we expect that there would be an increase in excess water pressure, increase in axial strain, upward migration of fine and moisture, and maybe the consolidation at the lower portion, which can lead to either the undrained yielding, which is you can reach the critical state and the soil fail, or you can reach the fluidization where the water content of the top portion reach the liquid limit, and there is a fine particle migration in the top portion, or the soil still stable throughout the application of the cyclic loading. Right, now, once we understand this mechanism of the fluidization and rain yielding of the soft subgrade soil under railway track, under the condition of the cyclic loading, then we try to find a way to mitigate this issue with the application of geosynthetics and vertical drains in railway track. Right. As you can see that the cyclic load induce the excess water pressure and upward fine migration due to the hydro gradient that make this shooting up into the ballast layer. Therefore, if we can provide additional drainage to ensure that we can reduce the excess water pressure development and also prevent the migration of the fine particle from the bottom layer and prevent the loss of this fine particle, then we should be able to mitigate the issue of mud pumping. In the past, we used the sand blanket for this purpose, and sometimes it's quite not so so environmental friendly, where you have to quarry the good quality of sand and try to use this in the railway track. Another option might be the use of the geosynthetics as a filter layer and the drainage layer, and therefore you can avoid using the natural material for this purpose. However, this application of the geosynthetics in the railway track is not the new topic. This has been applied in various embankments to provide the drainage, but quite often the issue lies within the railway track itself, that at the beginning everything seemed to be working very well. However, when upon the long-term operation of the track, it shows that this geosynthetics might create clogging phenomena where all the fines start accumulating and reducing the drainage capacity of these geosynthetics. And with this one, it's often create the further adverse effect because it acts like impermeable membrane, and therefore it prevents even the fine intrusion and make this track to become vulnerable to slurry because of the impermeable boundary that created by the clogged geotextile. And therefore, with this type of long-term issue, it can create the unstable track and also the excessive settlement. And these are the typical test conditions that we conducted to prove this concept and verify the performance of the geotextile. This is the apparatus that I mentioned in the earlier slides. the dynamic filtration apparatus where we can place the ballast directly on the top of the subgrade itself. As you can see that when we apply the cyclic loading, then as expected, we observe that there is the intrusion of the subgrade or the penetration of the ballast into the subgrade layer, and definitely is create the fouling condition between the ballast layer itself. And when we apply the geotextile at the surface of the subgrade below the ballast layer, you can see that the geotextile can act as a separators and provide additional drainage to this layer itself. However, we still have to look at the performance in the long term when this subject to the cyclic loading. Now, these are the test results. Compare these two conditions. The first one is the worst case scenario where you don't have drainage at all, because we call this as an undrained condition. And the second one is a free drainage where you just put the ballast layer above the subgrade soil. You can see from the excess pore water pressure response from the measurement. The excess pore water pressure response in terms of the free drainage, definitely the pore water pressure, excess pore water pressure develop and start decreasing with the number of cycles. This is because the particle migration between the ballast layer, and when you compare with the undrained condition where you don't have the drainage at all between the ballast as well as the subgrade, you can see that the pore water pressure cannot dissipate at all. It's maintained at the critical level all the way to the number of cycles. And also, in terms of axial strain, if you have the free drainage condition, the track settlement will be compromised. You can see that the axial settlement can be created up to 10%, whereby for the undrained condition, you can maintain the axial strain within 2%. However, with this 2%, the soil condition beneath the ballast can become sponge because of the excess pore water pressure development. You can see that either way it creates detrimental effects on the railway track stability. Now, the next phase of the testing program is we try to investigate the use of geotextile to prevent the fluidization of the soft subgrade soil. We have three types of geotextile. The first one, G1, is the specially designed geotextile where we have the blue filter media where the aperture opening size is less than 1 micron. And we have G2 where the AOS is approximately 60 micron and G3 is 75 microns. We try to investigate the performance of this geotextile under the long-term cyclic loading and try to find out the advantage where we have the filter media in the middle, and to find out whether it will be more efficiency to use G1 in comparison to the conventional geotextile G2 and G3. Right, now let's look at the result of the performance of the different geotextile. Let's focus on the performance of G1 and G2. You can see that overall the dissipation rate based on G1 is much higher compared to the measurement of the excess pore water pressure dissipation rate by G2. This is also emphasis in the performance comparison between G1 and G3 itself. You can see that the dissipation rate in G1 is much faster, and it can reduce the excess pore water pressure closer to 0. And the percentage reduction based on the excess pore water pressure measurement can be up to 90% based on the measurement here. Right. Now, in terms of excess pore water pressure gradient, which is the consequence of the different excess pore water pressure at different depth. You can see that the excess, the hydraulic gradient, for the soil sample with G1, the level of the hydraulic gradient is very low compared to G3 itself, confirming that there is very less pressure that can push the soil, the fine-grained soil, upward into the top layers in comparison to the G3 geotextile. And also we can confirm this one with the measurement of the moisture content of the soil sample after we subject this to the cyclic loading. You can see that the water content of soil sample with G1, the water content of the soil sample is almost constant throughout the depth, while the water content variation for G2 and G3 can be seen that the top part, the water content itself approaching the liquid limit, showing that in the long term, G1 can prevent the excessive hydraulic gradient near the surface of the subgrade, and also preventing the fine migration from this observation. Right. And also another benefit of the G1 geotextile is that it can also minimize the development of the axial strain in comparison to the axial strain developed under G2 and G3. We also have photos of the geotextile after the completion of the test. You can see that the color of the G1 geotextile after the application of cyclic loading is a bit cleaner compared to the other case where you can see the fine particle trap within the filter of the fabric, showing the advantage of the G1 for this type of testing. Apart from this, comparing the performance of the geotextile itself, you can see that the induced excessive hydraulic gradient that create within the depths can be minimized if we can have additional subsurface drainage that penetrate beyond the layer, beyond the surface of the subgrade itself. In this case, the prefabricated vertical drains has been installed at the shallower depth to facilitate the drainage of the water inside the soil mass, as well as dissipate the excess pore water pressure. We use the combination of the vertical drains as well as the geotextile to ensure that we can minimize the hydraulic gradient, the upward hydraulic gradient, and therefore create a better stability of the soft subgrade soil under cyclic loading. Here on the right hand side, these are the results of the excess pore water pressure with the number of cycles. You can see that with the combination of vertical drains together with geotextile, the excess pore water pressure can be reduced drastically in comparison to the test with geotextile alone. And also, if you compare the deformation aspects from this test result, they are in par together with the geocomposite alone. It can be seen that the use of vertical drains can facilitate the better dissipation of the excess pore water pressure at the greater soil depth within the shallow region of the soft subgrade soil, and therefore this might be another combination that we can consider if there is excessive issue with the mud pump site at certain location, and therefore we can further reduce the development of the excess pore water pressure along the depth of the soft subgrade soil. Now, when we consider the nature of the railway loading, from the previous test, we apply the cyclic load in one go, which means that we don't stop in between. We apply 100,000 cycles in one go and then measure the performance along the continuous number of cycles. However, if we consider the actual freight train operation, the nature of the usage of the track typically is we call intermittent, where you have the train run on the track, followed by the rest period where there is no train, and followed by the next service of the train. And we would like to investigate whether what's going to happen during this combination of the intermittent cyclic loading with the presence of the geotextile. For this one, we extend our test from the continuous cyclic loading. And we have conducted 4 series of tests to simulate the effect of the vertical drains with different drain spacing ranging from 1.2 meters to 0.6 meters for drain spacing, as well as we have the presence of the geotextile on the top of the subgrade, compared with the worst case scenario where we do not have any drainage at the interface between the ballast and the subgrade soil. And this is the intermittent cyclic loading condition where we have applied 33,000 cycles for each round of loading, and afterwards it's followed by the rest period around 14 hours, representing the usage of the freight track in Australia. Now, let's look at the measurement result of the effect of the intermittency. You can see that we have the excess pore water pressure measurement here and vertical strain in terms of time, as well as the cumulative number of cycles. The cumulative number of cycles is quite is excluding the effect of the rest period. You can see that in test D with no drainage, the sample fell upon the fifth cycle of the intermittent loading. And based on the excess water pressure measurement, you can see that the vertical drains can help in terms of dissipating excess water pressure. And from the test result, the combined vertical drains together with geotextile can further speed up the dissipation of the excess water pressure during the loading, as well as the dissipation during the rest period itself. Now, let's look at the effect of intermittency here. If we look at the proper presence of the drainage, you can see that the excess water pressure has increased with the deformation, and during the rest period itself, you can see that there is a dissipation of the excess water pressure during the rest period. However, during this time, you will not observe any development of the settlement itself within the soil sample. It's just like the soil sample experience the relaxation period where the water pressure just disappears. Right now, and also you can see that during the subsequent cyclic loading, the amount of the sediment start decreasing. This is because the reduction of the void ratio from the previous subsequent period that increased the yield stress and make the soil become stronger, and therefore with the next application of cyclic loading, the development of the sediment become lesser and lesser. And also, if you look at the excess water pressure response here, you can see that if the soil experiencing the settlement and subjected to the next cyclic loading, the excess water pressures tend to decrease because the yield stress and the void ratio of the soil, the yield stress increase as well as the void ratios decrease. With these two combinations, it makes the structure of the soil stiffer, and therefore it's cause the less excess water pressure development. Apart from that, you can see that during the rest period itself, the dissipation time become much quicker when the intermittency progress further away, and showing that the yield stress of the soil together with the reduction of the void ratio is the indicator where the soil can respond to the next cyclic load application. And overall, you can see from the vertical strain that regardless whether you have the presence of PVD or geotextile in combination, the final deformation is almost similar. Now, based on what we observed so far from the test and the effect of the intermittency, we can say that the reduction of the void ratio can link to the increase in yield stress, as well as the increase in the excess water pressure. The amount of the increase depends on the current yield stress of the soil, which means that if your yield stress of the soil is quite high, then there is a chance that the excess water pressure development can be less because the soil is much stiffer. And based on this observation, there are factors that control the soil behavior when it's subjected to the intermittent cyclic loading, which include the yield stress, cyclic derivative stress, which means that the how heavy of the axial load, as well as the in situ condition, including the confining stress that can be captured here. And based on the plot, we can have the stress part in terms of the three-dimensional plot showing the relationship between the void ratio, yield stress, as well as time. And based on this observation, we can come up with the new normalized factor, what we term it as normalized yield stress for cyclic loading. If you would like to have further look at this one, just check the publication listed at the bottom of the slide. You can see that the new index, where we call it as a normalized yield stress for cyclic loading, is the ratio between the current yield stress divided by the in situ vertical stress plus the cyclic derivative stress, or the amount of the axial load. And based on this normalized parameters, you can see that we can see the clear relationship between the excess pore water pressure together with NYCl. You can see the declining trend when NYCl is increasing and the excess pore water pressure is reduced, showing that with the stronger subgrade soil, you can minimize the increase in excess pore water pressure development. And also from the top right-hand graph, you can see the development of the yield stress together with the number of cycles within YCL. You can see that at the end, where there is no longer deformation in YCL approaching closer to 1. Using these normalization parameters will be able to help the practical application where you can, if you know the yield stress of the soil and in situ condition together with the next round of railroading, then you should be able to predict the future settlement as well as the excess pore water pressure for the upcoming train loading. Based on this concept, we provide the blended model where we consider the cyclic loading duration, the rest period, and the subgrade yield stress together with the normalization factor, and we combine them and then put it into the MATLAB. And these are the subroutine where we can use to ensure that we can predict the soil behavior under the intermittent cyclic loading. As you can see that we use the calibration from test A, and based on this, we apply this into the validation in test F, and showing that it can be used to predict the future deformation as well as the excess pore water pressure. To showcase the field application here, we have the site in the history where Professor Indarana has for the first time introduced the concept of prefabricated vertical drains to be installed underneath the railway track. And in this case at Sandgate, the vertical drains were installed at the shallower depth within the influence of the train loading. And with this site, we do not have time for the preloading, and therefore we expect to use train loading as the consolidation pressure. And once the track settling down, then we can reprofile the track, pack the ballast, and maintain the alignment of the track after the certain number of cycles. And in his paper, he's provide the equivalent concept to predict the deformation of the subgrade soil at the site. However, this during that time we still do not have the further insight how the soil behave under intermittent cyclic loading, because this is the real operation of the track, and therefore the nature of intermittency can be observed during the train operation. And he has provided class A prediction for this one. Based on observation in the lab, we are able to use this concept with the assumed constant intermittency patterns based on the experience from the site engineer Tim Neville, and we assume that the axle load is 30 tons, the train length is around 1.8 kilometers, and the rest period is around 30 minutes for this BC freight rail. And based on the site investigation data, the pre-consolidation pressure or the use stress is around 25 kPa, and based on that we can produce something closer to the what we observe in the field as well. However, you can see that the deviation of the data can be due to the operation of the track, and they assume constant intermittency rather than relying on the actual site data on the operational program. And also with this, after we can validate the proposed model, we can perform the parametric study, and you can see that with the closer drain spacing, we can have faster settlement rate. Or if you would like to mitigate the rate of settlement, you can make the drain further apart in terms of spacing. Right. Here is the conclusion from my presentation today. The mud pumping, we can say that it can be induced under the cyclic loading for the certain soil condition. This is due to the excessive hydraulic gradients, particle migration, as well as the increased water content. The geotextile with appropriate filter membranes can help in terms of dissipate excess pore water pressure, as well as reduce information, prevent the fine particle migration as well. And the consequence is, if you can reduce the development of the excess pore water pressure at the greater depth, then you can also reduce the upward gradient in the subgrade soil, and therefore you minimize the fine migration. And the composite geotextile together with the vertical drains can further reduce excess pore water pressure during the train loading as well as the rest period, and therefore it can enhance the track stability in the long term. The significance of this study, as you can see from today, that we can see that if we use appropriate geosynthetics in the weak subgrade soil and in rail track, you can reduce the cost of the installation of the natural compacted sand, and also we can control the risk of the mud pumping with the increased track safety. And therefore, we can extend the life of the track and minimize the frequent track maintenance schedule as well the cost. And at the end, just want to acknowledge the continuous support from the Austrian Research Council, distinguished Professor Buddhima Indrana, who has been inspired and lead this research project in the past 10 years in terms of initiating the concept of vertical drains under the cyclic loading, and also the PhD students as well as the research fellow, including Joseph Chachika as well as Bin Huang, and the strong and active support from Global Synthetics as well as the partner investigator Andy, who's provide further insight and the support during this challenging research topic. And I would like to acknowledge the support from ARCRI, SMEC, ARTC, Sydney Trends, and other technical staff who make these tests become possible and showing the further insight of this analysis. Thank you so much for listening to me today.
Thank you very much, Professor Cholachat. It's while I was part of some of what you've presented, I hadn't quite appreciated how much further you've gone with the research since I dropped off. So yeah, that's really interesting to hear. We have gone a little bit over time, so I'm going to have to keep the questions a little bit limited. One of the ones that came through was, and you may not be able to answer this, is quite a tricky one. You talked about clogging with different geotextiles. You know, so standard geotextiles, heavy geotextiles, and geocomposites. Did you have a kind of ratio of how much they clogged in terms of one type to another type? You know, was it linked to pore size? Was it linked to opening size, particle size, that kind of thing? Or is that not something you really investigated?
Now it's as far as it shows that the composite geotextile work very well under cyclic loading. It prevents the fine particle in comparison to the both other geotextile. However, as you said, it's still beyond the concept where we start varying the opening size and see the effect between the size of the fine together with this. I think this has to be subjected to further investigation. But based on the product that we have, we try to be strategic to select the product where the company recommend this to be used in terms of providing additional drainage and provide a better stability for the subgrade soil for other type of the embankment construction.
No, I totally understand that the subject of clogging in geotextiles is actually quite broad. It's not just limited to rail and infrastructure. So maybe that's a new program for you, Cholachat. I think we'll probably leave it to one more and the rest that we'll answer online. This is an interesting one, and it was about subgrade impact. So when you're using your PVDs and you're using your filter geotextiles, Obviously, there's a benefit that you're taking the water out of the subgrade, which is stiffening up the subgrade and stiffening up the foundation. Is there a potential risk, though, that it dries it out so much that it causes cracking and decimation, and then potentially the trap moves because of a different way, i.e. it's gone too far? Is that something
No,
you've experienced?
normally the change in the moisture content in the subgrades is to dry out is very rare unless you subject very long drought period. Quite often it's the opposite, that you subject this tract to the maximum rainfall and the subgrade can become saturated and it create the mud pumping issue. Yeah. And when the subgrade dry out, definitely it provide better shear strength and less deformation as well.
Yeah, no, that's perfect. Okay, so we have run a little bit over time today, so we're probably going to close it there and we'll do the rest of the questions online. To all of the, say, young students and all any professors, university guys here, I say we are approaching summer and we would love to try and help graduate engineers, graduate students, PhD students with job shadowing and so forth. It's free of charge and it's a great experience to get exposed to geosynthetics that you don't necessarily otherwise get exposed to. So please jump online, have a look on the ASICS website, and we look forward to seeing you all again in next month's webinar. Thank you very much, Cholachat, and thank you
My
for all
pleasure.
that attended.
Thank you, Professor. Cheers.
Bye.
You need to end it, Roger.
And webinar.